but when k is 0, the sum of the exponential term. Oh, it does, right? The exponential term, because you have to sum over an exponential term that's e raised to 0, so you have the sum of 1, which goes to infinity. So maybe.
But computer won't see it, right? Will not be able to handle that. It should complain instead of multiplying an infinity and a 0. Right? It shouldn't.
But maybe not, because I'm not using it as an exponential, because let's put it into imaginary, so it's a cosine. The imaginary for both is 0 at 0. The only one that's not 0 when k is 0 is the real scattering amplitude for the void circles.
Let's stop. Good. Thanks. Good, is this here?
I think I know why it's not complete.
So about homeworks, I was thinking of making 2 homeworks, one due this Friday and one in the last Friday, but I changed my mind. I'm going to have only 1 homework due that will be on Wednesday of the last week of classes. Okay. Just because it's a little theoretical concepts that you guys have had enough homeworks.
So it's due in 2 weeks.
Yes. But if we include Thanksgiving, also. So 1 week working from Wednesday. This is good. And then we have the final exam. I think this was earlier supposed to have been November 20th, so make sure we change that. This will be Friday. This will be take home. Made available earlier in the week. Today, I want to introduce a general idea of what we mean by conservation law. Conservation law. And let's begin with Maxwell's equation, and we will derive the simplest conservation law, which is the conservation of electric charge. The way we know it, electron, we cannot create a charge. Right? We're not talking about the relativistic scenario where matter antimatter is created. That's not what we're talking about. But a charge itself, even when things are created, that remains the same. If you create a positive charge, a particle with a positive charge, you have to create a particle with a negative charge. So where does that come from? So what's the basis for that? So let's go back to Maxwell's equation. So Maxwell's equation tells us that the divergence of the electric field is equal to charge density. Then we have the divergence of the magnetic field. Similarly, should have been magnetic charge density, but this is equal to 0. So we say that that's no magnetic charge around us. They all come in pairs, positive and negative. And the curl of the electric field is equal to negative time derivative of the magnetic field. That means the change in magnetic field can create curl of an electric field. And similarly, crossed with H is equal to time derivative of the electric field plus J. The D is the same as the quantity that shows up here. So D is equal to epsilon times E plus, and D is equal to mu naught times H. We're not having materials around. It's just D. If we have a material around, then this becomes epsilon naught instead of epsilon naught. Here, epsilon. Well, that's this is all the Maxwell's equation we have been dealing with, except that we were trying to avoid these terms. Right? Any time dependence we were trying to avoid. Now we have everything. So in that sense, we have a complete set of equations. And let's begin by multiplying, or not just multiplying, take the derivative of the first equation. So we can manipulate this equations. So let's take the derivative of the first equation with respect to time. Remember, this charge density can depend on R and T. And similarly, so that's we have manipulated the first equation. Same thing, let's do the fourth equation, but this time let's not take the time derivative. Instead, let's take the divergence of that equation. So that's divergence of L crossed with H is equal to divergence of the time derivative of the displacement field, and that's plus divergence of the current. And first thing we notice is that this is 0 because this is a curl, and a divergence of a curl is 0 because this is an antisymmetric quantity in this derivative, and these two together is a symmetric quantity. We clarified that that will be equal to 0 all the time, as far as it is applying operating on the same quantity. If it is applying on a different quantity, then the symmetry is lost, then it doesn't apply. So that's equal to 0. Further, this is equal to the second term here even though they don't look exactly the same, but the time derivative and the gradient they commute with each other. The order of their operations doesn't matter. We can interchange them. So we can put this in there. So together, this implies 0 is equal to time derivative of the charge plus the divergence of the current density, and instead of writing equal to 0 on the left, so let me just write it on the right. This we will say implies that charge cannot be created or destroyed. Why do we say that? So let's interpret this a little bit more. So this simply says that time derivative of charge plus divergence of another vector is equal to 0. So let's for a moment, even though this is 0, let's actually place something s of r comma t. This is of course 0, but let's analyze something more general. So we have an equation. So this is, we will call this a continuity equation. This. So we have the equation. Let's explicitly write this. Time derivative of rho comma t plus the divergence of current. So this is charge density. That's the current density, and this is as we see it, current density is the the motion of charges is what causes current. So we will call this the flux of the current density. So the vector that shows up here in general will be called the flux of whatever shows up here. So that will be our notation, but let's first analyze this and we'll come back to the notations also. So we are analyzing this problem. Notice this is a scalar. And also this is, I call it S because it could be a source of something. Okay, so that's what we have. So let's integrate this quantity. So we can integrate over over what? So let's say over a closed volume V. So V is a closed volume. So pick an arbitrary volume which has a boundary around it, and we do this integral for each of the terms. Now that's equal to integral dq r s of t. The time derivative can move around. So d cube r times integrated over this charge density is equal to, this is d cube r times charge density. We have integrated over r over a fixed volume V. But what is that equal to? That's actually the total charge in that volume V. But it changes with time. Notice that it changes with time. So let's think of this. So we have a closed volume V, and it also has a surface, right? So this is a surface, there's a boundary of this volume. So this is a three-dimensional volume, and once you integrate this, this tells you the total charge, and this can change with time. But then we ask, how can the charge inside this volume change? What is the source of this changes? How does it change? And that's what this equation is about. This equation tells us what quantity decides this charge. And this is more general than what we are talking about. It could be any equation in any other context, and we can still have the same interpretation. So this could be some scalar quantity. Later we will see it can even be vector. Some quantity whose time derivative is equal to, important thing is the divergence of another vector quantity is equal to a scalar. If I integrate this out on the volume, I get something that is dependent only on time. So this is, here we talk about what's the charge inside this volume as a function of time. So this is equal to dq by dt. How charge changes with time. What is the next quantity? Here, this is equal to, that said, divergence of a vector and then integrated over a volume. We use the divergence theorem. We can immediately switch over to the surface. This is a closed surface integral. That's dA. So everywhere there is a j, so that could be a j coming out of this. So that's it. So these are all j's. So some vectorial distribution of j. And why that's starting from the point here, even though there's a current densities, we don't ask that. There could be some reason why that's originating from that point. So it's g. This tells us how much charges are moving out of this boundary. Right? So that's the interpretation here. A reasonable interpretation is that this is a country, this is a population. So think of this as a population density. And this tells you the population as a function of time and how many people are crossing the boundary of a country. That's the flux of the population. So this will be interpreted as, so this will be the flux. In this case, we are having charge. So this is flux of charge moving across the boundary of V. The boundary of the volume. But it's also possible that, especially when you think of it as a population, people can die or take birth, right? And that's the interpretation of the right side. That this is the source or sink, and we will keep it as it is. This is d cube r. Let me say that is s of t, right? That's a function of time. S. So this is capital S of t. This quantity is a function of time alone because we integrate out on the r. So this is the source or sink of charges, whatever is on the left hand side. So the interpretation is, again, we have a volume V. The change in the rate of change of the charge depends on two things, only two things. How many are created or destroyed, that's this term, or how many are leaving the boundary of the charge. So that's the only two ways you can get it. And that's what is called the continuity equation. And this could be anywhere. You don't have to be talking about an electricity and magnetism. Any equation of this kind has this interpretation. What we have here is in electricity and magnetism is that the source is equal to 0. What we have learned, the Maxwell's equation imply, like this is not that we created this. If Maxwell's equation are true, then it tells us that this is equal to 0. So this implies then charges, the source and sink of charges is 0. And what's the difference between this equation and this equation? This is true for a macroscopic volume. This equation is true for at every point. You can always say that, oh, maybe this is a big volume, but inside there is a creation, but then it's destroyed right next to it. But that's not, that is taken care of when you say that this is at a point. At every infinitely small volume element, which is what a point means in our coordinate system, this equation is valid. So this is a local statement of the same conservation that we are talking about. So in that sense, it is a completely fundamentally true statement that charges cannot be created or destroyed because S is equal to 0. If it was not 0, then it's not. So this implies that charges cannot be created or destroyed. Which means to say that there's a good chance that whatever our universe, the charge is, that stays static, right? That doesn't change at all. But you might be, even if you take an atom, so the charges are, number of charges are neutral, right? So on an average, it seems reasonable. But at the same time, if you go back in time, it is also true that there is an asymmetry in the following sense. When you think of matter and antimatter, right, there seems to be a lot of matter around us. Like we don't see a lot of antimatter around us. So if you stretch this all the way back, one would expect this to be true for antimatter. Also varies all the antimatter, and that remains sufficient. Like we don't have, the expectation is that from the current understanding that there should have been equal amount of matter and antimatter, but we obviously see a lot of matter. It's possible that in our corner of the universe that's the case, but it doesn't seem like. All the observation seems to suggest that there is more dominance of matter over antimatter. Then the question comes, where did all of them go? Right? There was some symmetry breaking somewhere, and it is not understood as of now. That remains an open problem as to why there is so much matter over antimatter. So yeah, so look it up, maybe. Yes, the extra credit maybe. So matter, antimatter. So keywords are matter, antimatter, symmetry. And in fact, go ahead and look up CP violation. C means charge, P means parity. So there's some, it's discussed in the context of violation of a statement. Okay. So again, what we want to keep in mind is that whenever we see an equation of this kind, without the 0 in here, it would mean that this will be a quantity here, this charge density, J will be interpreted as the flux of the charge density. Maybe clarify, mention that. So this is d rho over dt plus delta J is equal to S of T, so which is equal to 0. So J here will be interpreted as flux of rho, right? Where rho is charge density. Right? So J is of course current density, but another interpretation is that this is a flux of charge density, and S is source or sink of rho. Similarly, now what we are going to do, our whole approach now is going to be how many such equations can we write? So can we manipulate this and rewrite something else that has the same quantity? In fact, we are going to write for energy. We will find out what's the energy density associated with Maxwell's equation and do something like this. Then we will be able to talk about flux of energy and source of energy. And same thing with momentum, right? We will talk about what's the momentum associated with electric and magnetic field, and what is the flux of momentum, what is the source of momentum. We can talk about angular momentum, and there are lots of physical quantities we can build like that. We will stick to energy and momentum for now. So let's go back to Maxwell's equation and process. So notice what we did was we took the first equation, multiplied by d by dt, and did this. Actually, before I go there, one can also ask, what about magnetic charge density? I worked with only these two equations, right? What if I do the same thing with these two equations? I can take the time derivative here and take the divergence here. Like maybe we will learn something. So let's quickly do that. So take the second equation, and this will be time derivative of the divergence of the magnetic field. This should have been the magnetic monopole charge density, but that's zero, right? That's zero. And the second equation tells us that take the divergence dot curve of the electric field is equal, or let me write it as plus d divergence. Right? So dB by dt is equal to 0. Right? Ideally speaking, this should have been the magnetic monopole density. Right? This is equal to 0. This is equal to 0. And this should have been the current density. So this will be the flux of magnetic current density, which is also equal to 0. But since these two are 0, you can substitute this in here, that's 0, and this is already 0. So this doesn't give you any information if these two are 0. If these two are not 0, we would have learned something about the magnetic monopole charge conservation. And the expectation is that if it exists, they will be conserved too, because Maxwell's equation comes true. And if this is how they appear in the Maxwell's equation, then they will be equal to 0. And but in the absence of magnetic poles, this is just an identity statement, so we don't get anything. So let's go back. We also have, in addition to Maxwell's equation, we also have the force equation due to Lorentz, right? Lorentz force equation is Q times E plus QV cross V. That's for a point charge. Point charge Q. But it is nicer if we could think of a force acting on a charge distribution. So let's divide it by volume. Any arbitrary volume, and this is volume, that's volume. Interpret charge per unit volume as charge density, force per unit volume as force density. Now this is a function of R and T, that's force density. That's equal to charge per unit volume is charge density times the electric field plus charge times velocity is current density. That's J cross with B. Let's multiply this with velocity. We could have actually done that here itself, or let's say we multiply it with J. Is that what I want to do? No, that's not what I want to do. Let's first start with velocity. Force started with velocity. What's the in classical Newtonian physics? What is force started with velocity? Power, right? Yeah, power. That's good. So that's exactly what I want. So then I'm good. So I should keep this. But actually, I want to divide the volume later. So let me redo this. So first, I want to multiply by velocity and then do the division by volume. So this is force started with velocity. That's your Q times V started with the electric field. And V crossed with, or V dotted with V cross B will be 0. Because the cross product is perpendicular to the vectors it is built out of, so that's equal to 0. Then we divide out by volume. That's per unit volume, and that's per unit volume. This is power, so this is power density if you want. Power per unit volume, and it can change with time. So this is power per unit volume. That's equal to, this is charge times velocity divided by volume, that's current density dotted with electric field.
Is the power density a vector?
Oh, no, it should be a scalar, sorry. Thinking wrong. Yeah. So thank you very much. So that's because this is a dot product, it should be. Thank you. So that's good. Now, and until here, this is just a construction. We started with a force, we are talking about power, but now we use Maxwell's equation. We use Maxwell's equation to replace the current density using the fourth Maxwell's equation. Right? So current density shows up here. So let's write this as del crossed with H minus of time derivative, the displacement vector, dotted with electric field. That's good, but this we would like to do a little bit more. If there was a magnetic monopole, this will have something in here. And since it's not there, it is 0 as it sits, but we would like to keep that symmetric term. So as of now, since it is 0, I'm adding, I can always add a 0. So what's the motivation is to write a conservation equation, right? So I'm just manipulating equations here. So let's write the same equation here. So this came from this equation here, which is 0, right? Del cross E plus dB by dt. That's a 0, right? That's according to Maxwell's equation, this is 0. So I can always add that to it. But as a vector, I want to dot it with something, and I will dot it with H. I'm trying to do an exactly symmetric scenario there, or I'm trying to build a symmetric scenario there. And since it's a 0, I can add or subtract, right? So I'll subtract. That is so that I can see these two terms together as a negative quantity. Okay, so that's fine. So now let me collect these two, the time derivative terms together and the curls together. So I have del crossed with H dotted with electric field minus of del cross E dotted with the magnetic field, and we have these two terms, which is minus of time derivative of, let's bring out this epsilon naught in here. So that's an epsilon naught. So we write it in a certain way. Oh, let's do this slow. Dotted with electric field. I use parentheses so that there's some confusion. Minus H. Okay. Let me process this a little bit. Notice that time derivative of d dotted with E is equal to, there is a dielectric permittivity of vacuum coming up, so it's epsilon naught, and time derivative of electric field dotted with the electric field itself. But I can rewrite this, since there is a symmetry in this E. Notice that this is the same as epsilon naught times time derivative of E dotted with E. Because when I take the time derivative of this, I get this quantity dotted with E. But then this can hit on this also, so it brings in the same quantity again. So I divide it out by half. Notice that it's like saying derivative of something d by dx of half x squared is actually, how much is this? 2x, so it's just x. Is that a good analogy? I guess so. yeah, try to see the, like, because of the symmetry, the factor of half is needed in there. I can put the epsilon naught back in there. So this is d by dt of half of E divided with D. So that's same thing works out with the magnetic field divided with H is equal to time derivative half of H divided with D. And finally, we have this curl equation in here. So let's do the following. Let's see what is equal to del crossed, no, the dot with, the dot, right? The del dot with E crossed with H. Right. So the motivation is that that's probably the same as this. Let's see, what is that equal to? So that's equal to, you can either hit the first equation or the first field or the second field. When it hits the first field, but I have to take the cross product first, right? So let's go to indices. So this is epsilon I j k and del I j h k. So indices work very well in this case. So this is either it can hit E or K, so that, and the cross product and the dot product are contained in this set symbol. And now make the distribution. I j h k plus. It can also operate on the second j but that's nothing but the cross of electric field dotted with H, right? Because I and J are the first two terms, so that's del cross E dotted with H. And this one is, there is I and a K, so I want to move this once to the right. That movement gives me a sign, that's minus of E dotted, or let me write first write that, yeah, E dotted with del crossed with H. Notice the negative sign comes from the interchange of the indices in the Lewis-Evita symbol. What is that equal to? So that's exactly the same as our first expression, except that it is overall off by a negative sign. So this seems to suggest that this is equal to a negative divergence of a quantity E crossed with H. And here you have minus time derivative of half E vector with D plus of H vector with V. Let's rewrite this. Let's take all this to the left hand side. Half E dotted with E is half H dotted with E. It's time derivative of some quantity is, or plus the divergence of another vector. Notice the comparison with the continuity equation that we wrote. And has something to do with power. This term here, that's nothing but epsilon, half epsilon naught E squared. Where do you see this? Where else have you seen this? Energy, that's correct. Of what? Give an example where you've seen this before. And EM wave, yeah, that's correct. Yeah, that's very ahead. That's good. Somewhere in electrostatics, maybe? So if you, that's good, the example that you gave is very good, but it's just that it's ahead of the game, it's in the sense, electromagnetic energy density. But if you were to do a capacitor problem, you do have this negative charges here and positive charges here, and ask how much energy is stored in the capacitor. First of all, where is the energy stored? One could ask, and it is stored in the electric field. All the energy is actually in between the capacitors in the air. So it's in the form of electric field. As you put charges in there, electric field increases, and this electric field contributes to a certain amount of energy. And that's energy density, energy per unit volume. So it comes out to be energy per unit volume of this capacitor, which is energy density. So this, and the same thing, where would you store, how would you store magnetic energy? Solenoid, exactly. So capacitor stores electric energy. So similarly, if you were to have a solenoid, there is magnetic field in there. So that's your V, and the energy stored in that is half mu naught V squared. That's exactly the second term. And in electric circuits, you keep like you can make this oscillate. You can change the energy from here to there, so you can do a lot of interesting things in that. And this we interpret as the energy density, electromagnetic energy density. So we are going to write this as du by dt plus this quantity we will say is S plus power. We can go back, and this was J dotted with E, right? So go back and write it as J dotted with E itself. If we don't want to confuse ourselves. So that's equal to 0. So let's see what the interpretation is. U is electromagnetic energy density. That's the, we just have to identify that. From that point on, what is S? We don't have to give any definition. This is the flux of this quantity. How much energy is going from the boundary, right? How much energy is escaping or incoming from the boundary is what the flux is. So this is flux of electromagnetic energy density. But it is also has a name, right? Flux of energy has a name associated with it. And if you remember your undergraduate things, this is called a Poynting vector. It's not the spelling, this is the name of a person, but since flux actually points in a direction, very timely name in a sense. So Poynting vector. And there is a third quantity here, right? So is energy conserved? Is the electromagnetic energy conserved? No, it is not conserved in a given volume. You can lose or gain energy according to this. So how do you lose or gain energy? You can make the charge move, right? An electric field can make the charge move. That means to say you lost your electromagnetic energy into the motion, right? So that's how you lose energy. So this is the work done by electromagnetic by electric field, right? That's really electric field. By electric field to move charges. That's that. But all this together has to be equal to 0. So the basic idea is that we have identified u, we have identified the pointing vector, and with this we will do a few things. But before we have to proceed and get the momentum also similarly. What is the momentum density for the electromagnetic fields? And if possible, if you have time, we will do the angular momentum also, but that's relative. And then how can we use this? Where does this show up? Like it should be possible to use these quantities to do some calculations. Okay, so let me stop here. Thank you.